Okay, so last time we already have the this example for isothermal heat treatment. Okay, so in this case, this isothermal transformation with the initial composition of 0.45% of carbon content. Okay, and we have to sketch and label the time, temperature, paths to produce the following macrostructures. And last time we already know the this path of the 42% of the pro-refractory ferrite and the 58% of coarse pearlite, right? And so today we're gonna to find the time temperature path of 58% of fine pearlites and the 50% of a bentonite structure. Okay, so let's look at the TTT diagram. Okay, let's look at the TTT diagram here. So for the 50% of fine pearlite and 50% of bentonite, we have to figure out its this time and temperature path from this TTT diagram, right? So initially, isothermally heat treat at 190 Celsius, okay, and 50% of the austenite transfer to fine pearlite. Okay, initially we isothermally treat at 590, right, from the temperature above the eutectoid temperature, right? So this temperature is eutectoid temperature, right? This temperature is TE. Okay, and then isothermally heat treat at 590, right? So temperature will decrease to 590. Okay, and the remain for a long time, right? And the austenite starts to transfer to pearlite at this moment, right? At this moment, right? During the time remain and the pearlites form continuously. Okay, continuously. So when this time keep going, and this pearlite forms continuously. Okay, and at this moment, then at this point, the pearlite structure is completely formed. Okay. Okay, so can you realize how this this heat treatment for the 50% of austenite transfer to fine pearlite? Okay, and when this time to reach a specific time here, right here, at this moment, that's mean the 50 of austenite and the 50% of pearlite, right? And at this point, that's mean the 100% of pearlite. Okay. And then isothermally, he treated at 470, right? So we drop the temperature to say 470. And this point is 590. It's 450 Celsius, right? Therefore, drop the temperature, and we remain the temperature for a long time, right? Okay, and all remaining austenite transfer to bentonite, right? So the remaining austenite is 50%, right? At this point, it's 50%, right? And when the temperature drops to 470 Celsius, and the time remains for longer, and the remaining austenite transferred to bentonite. Therefore, we get 50% of pearlite and 50% of bentonite. Okay. So so that's the heat treatment path, the time and temperature path for 50% perlite and 50% of bentonite. Okay. So finally we got a 50% and 50%. I'm sorry, it's not this one. Sorry. So at this point, we get a 50% of the perlite and a 50% of bentonite. Okay, at this point. Okay, because the remaining austenite transfer to bentonite. Okay. Okay, so for the part C, the 100% martensite rapidly changes to room temperature. Right, so you can look at this TTT diagram, right? Initially, temperature is above the TE, right? The initial temperature is right here, and this is TE, say 127 Celsius. Okay, and if we drop the temperature rapidly, that means the trenching process to room temperature. So the time temperature pass is this one, right? Just drop the temperature rapidly. Okay, the pass C. We get a martensite, 100% of martensite. Okay, 100% of martensite. Okay, so as we already mentioned, if this temperature is the continuous cooling, in this way. Sorry, continuous cooling in this way. What we got might be at this point, at this moment, the arsenide starts to transfer to perlite or bentonite. Okay. Okay. So for the pass D, 50% of martensite and 50% of austenite. What's its time and temperature pass? To rapidly change to 290. Okay, just drop the temperature to 290, right? 290 is right here. 290 Celsius, and hold this temperature a long time. Okay, we got a 50% of martensite. Of course, in this region is austenite, and sorry, I just list them all the things. Okay, so for the pass D, right, and in this region is austenite, right, and in this region is 50% of martensite, right, 50% of martensite. Therefore, the temperature reaches 290 at this one, this point. 290, if 50%, these microstructure, we have found 50% of martensite and 50% of austenite. Okay. Okay, so let's look at the mechanical properties that were influenced by the carbon content. So we already knew the phase diagram of the iron carbon system, right? So when this composition is less than 0.76% of carbon, the structure is called the microstructure is called the hyperreactor, right? And when the composition is greater than 0.76% of carbon, and its microstructure is called the hyperreactor, right? Hypo and hyper. And what's their mechanical properties? Okay, so we just look at these two figures. One is for the hypo and hyper with tensile stress and the urine stress. Okay. Okay, so this tensile stress and urine stress increases with increasing the carbon content, right? Increase with the carbon content. Okay. Therefore, its ductility should decrease with carbon content, right? Therefore, its ductility or its elongation decreases with carbon content. Okay, so remind that what's the reason why that hyperstructure is stronger than hypostructure from the microstructure point of view. Why? So from the microstructure point of view, so we can look at the figure for the hypoeutectoid structure, right? It's micro constitute is the pearlite and the ferrite, right? Ferrite is soft, while pearlite is hard, metal hard, right? Okay, so how about the microstructure of hypoeutectoid? Its micro constituent is what? What's this microstructure? Consists of the pearlite and the cementite, right? Pearlite and cementite. Okay, pearlite and the cementite, right? And for these two structure, both have this pearlite structure, right? However, for the hypostructure, one of this its microstructure is ferrite, which is much softer than cementite. Okay, therefore the hyperstructure is always or much stronger than the hypostructure. Okay. Okay, so the mechanical properties of the fine pearlites versus coarse pearlites versus sapphirite. Okay, so the sapphirite is the sapphiric, the wrong structure, right? Okay, so we can compare with these three different type of the structure: fine, coarse, and sapphirite, with the hardness, right? Corresponding to the carbon content. Okay, so we can see this the 0.6. Okay, so the same that the hyperstructure is stronger than hypo, right? However, the fine pearlite is stronger than the coarse pearlite that is stronger than sapphirite. Okay, and for the ductility, the sapphirite, is more ductile than coarse and fine pearlite. Okay, therefore we can control its mechanical property, hardness, ductility, unit stress, tensile stress, with the carbon content. Okay, with the carbon content. Okay, so usually the higher carbon content with higher mechanical properties. Okay, and the fine pearlite has the higher mechanical property or is stronger than coarse pearlite and the sapphirite. Okay. Okay, so the mechanical properties of fine pearlite versus the martensite. Of course, there's huge difference between the martensite and the fine pearlite. Okay, and the martensite will be the hardest compared to fine coarse pearlite and the sulfurdite. Okay, so there's huge differences. Okay, between the martensite and the fine pearlite. Okay, for the hardness for the martensite, it's much larger than the fine pearlite. Okay, so what's the approach to adjust the to modify the mechanical property of martensite? Already mentioned in the previous course, by tempering, right? By tempering, and the mechanical property of the martensite can be modified. Okay, want to reduce its hardness, reduce its tensile stress, unit stress. Okay, just by tempering process. Okay, say the tempered martensite, heat treat martensite to form tempered martensite. Okay. So tempered martensite less brittle than martensite, and tempering reduces internal stresses caused by trenching. So as I already mentioned previously, right? If you want to modify the mechanical property of martensite, right? You can just temper this martensite, right? Depends on what's the mechanical property you desire. Okay, therefore for the tempering temperature versus the mechanical property, tensile stress, unit stress, and the reduction of area. Right? Therefore, from this figure, you can realize that, okay, we can adjust, we can modify this mechanical property of martensite. Okay. Okay, from this microscope point of view, you see the tempering process extremely, the tempering produces extremely small the cementite particle, right? Cementite particle surrounded by alpha ferrite. Okay, so you can see the spherical, this extremely particle is a spherical, it's the round shape, right? So do you still remember the sulfurdite structure? Right, the sulfurdite structure has the lowest mechanical property, right? Unit stress and tensile stress. Okay, and the alpha ferrite is soft. It's soft. Okay, therefore, by tempering process, the mechanical properties of martensite can be reduced. Okay. Okay, so there's a summary of the possible transformation. Okay, we're starting from the austenite, right? The alpha solid solution. Okay, with different cooling rate, and the different phase we're from, we're transferred. Okay, depend on different cooling rates. Okay, for slow cooling, for the slow cooling rate, the phase will transfer into pearlite. So pearlite, what is a pearlite structure? Is alpha and the cementite layer structure, and the proeutectoid phase. Okay, proeutectoid phase. Okay, for the moderate cooling rate, the bentonite will form. The bentonite phase forms. So what is the bentonite phase? It's alpha ferrite, right, and the cementite particle. Okay, the cementite particle. Okay, and through the trenching process, that means the rapid cooling rate, and the martensite structure form. It is BCT phase or the BCC phase. and the transformation is diffusionless. Diffusionless. Okay, it's diffusionless. So what's the structure of the martensite? You still remember that? It's a needle shape, right? It's a needle structure. Okay. So the mechanical property of martensite can be modified by tempering. Okay, by tempering. Therefore, by reheating. Therefore, the tempered martensite, whose structure consists of alpha ferrite and a very fine cementite, right? Fine cementite particle. Okay. Okay. Therefore, we can compare the generously you can compare the mechanical properties with different phase. Okay, with different phases. So the martensite always has the highest strength and the lowest ductility, right? The tempered martensite, well, whose mechanical property is not stronger than that of the martensite, right? And for the strength, the Pearlite is well stronger than fine Pearlite. Okay, fine Pearlite, and fine Pearlite was stronger than coarse Pearlite and sulfurite. Okay. Okay. Okay, so alloy strength by exceeding solubility limits. Coherent precipitate, especially for non-ferrous and stainless steel. In coherent precipitates, the precipitates crystal planes are related or continuous with the crystal plane of the matrix. This helps block more dislocation. Okay, therefore for figure A and B, which one is coherent? Precipitate A and B, which one is coherent? So what means coherent? Coherence, what's the definition of coherence? Coherent precipitates, right? Those precipitates crystal plane or lattice plane are correlated to or continuous with the crystal plane of the matrix. And what's the reason why this helps block more dislocations? So can you explain this phenomena? Why? I want to know why. Can you explain that? Can you explain that? Okay, so the figure B is coherent. Okay, so for the figure B is coherent. Okay, for the figure B is coherent. That means the crystal plane or lattice is continuous. Okay, so the lattice continues, and the lattice is continuous, or the a crystal plane is continuous. Okay, it's continuous. Okay. For the non-coherent precipitate, that the precipitous crystals are not related or are discrete with the crystal plane of the matrix. Okay, therefore for this figure A, it's non-coherent. Okay, it's non-coherent. Okay, right? So you can find there are two crystal structure, 1 and 2, right? 1 and 2. In this case, its ability to block the dislocation movement is weak. Why? Why? right? So let's look at the coherent precipitate first. Okay, so because the crystal planes are continuous with the crystal matrix, therefore, when we have the, for example, we have the dislocation here or here, right? So it will move to here. Oh, it will stop, right? Because this lattice distorted, right? Distorted, right? Therefore, the dislocation movement will be stopped, blocked. Okay, will be blocked by this continuous lattice, distorted. Okay, distorted. Okay, the same this dislocation will stop here. Will be blocked here due to the due to the continuous lattice distorted. Okay, and in this case, for example, if there's a dislocation movement here, when it reaches this, well, maybe for the non-coherent precipitate has the ability to block the dislocation movement a little bit. However, these two crystals are independent, right? Therefore, for this dislocation, I can still move, right? Because the pass here, or the pass, right? Pass here or pass here. Okay. These passes are not having so much barriers. Okay. For the continuous crystal structure, dislocation is easily to block by those crystal lattice. Okay, for this non-coherent, the dislocation just move directly, or maybe the dislocation will feel some, retarding, however, it can still move. Okay. Okay, aging precipitate hardening applications for non-ferrous. Okay, aging or precipitate hardening is produced by a sequence of phase transformations that leads to a uniform dispersion of nanoscale precipitates in a more ductile matrix. Okay, it is used to increase yield stresses of many alloys via simple heat treatment. Aluminum, nickel superalloys, and titanium alloys are age hardened for use in many applications. And disadvantage is that the age hardened alloys can be used over a limited temperature range. At high temperature, the precipitate began to grow and eventually dissolved. Okay. So let's look at what's this age or precipitate hardening. Precipitate means the second solidified form, right? Second solidified form. And this precipitate can be coherent or non-coherent, and coherent precipitate has the ability to block this dislocation movement. Okay. So what's this? There are 3 steps in age hardening heat treatment. So you guys must familiar with this phase diagram, right? This is aluminum ridge of the aluminum copper phase diagram. So at the point 1, it's the alpha solid solution, right? It's alpha solid solution. Okay, it's about maybe 4 weight % of copper and the 96% of the aluminum. Okay, of aluminum. Okay, therefore, if we want to age hardening this alloy, the process is to decrease the temperature to 0.2 rapidly. So what this process called? It's trenching, right? It's trenching. Therefore, from the 0.1 trenches to the point 2. So what's the phase we form? The Martensite, right? The Martensite, right? The Martensite. Okay, therefore from the point 1 to point 2, by trenching, the phase is still uniformed with alpha phase and alpha solid solution. Okay, alpha solid solution. Okay, and from this point 2, heat treat to certain temperature, raise the temperature to say, in this case is 100, maybe 130 Celsius, right? For the aluminum copper alloy, which is aging at 130 Celsius. And remain for a long time, and the precipitate will form in alpha solid solution. Okay, for alpha solid solution. Therefore, we can see the structure here for the point 1 is completely alpha, right? Right, and drop to trench into point 2, right? We got an alpha with theta phase. Okay, and then we age at 130 Celsius. The theta phase will precipitate. Okay, will precipitate. Okay, so this theta phase is precipitate from aging hardening. Okay, and we need a longer time for aging. Okay, for aging. That means you have to keep at 0.3 for a long time. Depends on your application and depends on your process. Okay. Okay, so the microstructural evolution in age hardening. So the step 1 is solution treatment. Okay, alloy is above the surface temperature till a homogeneous solid solution is produced with no phases or microchemical segregation. Okay, so that's mean the point 1 in the previous phase diagram, right? Point 1. Okay, in step 2, trench. Solid solutions rapidly cool, so atoms cannot diffuse to nucleate sites. This forms a non-equilibrium supersaturated solid solution. Okay, so this point is point 2. Right? For aging, the solution is heated at a temperature below the surface temperature, or say the aging temperature. And what's the exact aging temperature is? Wow, it depends on your alloys and your process. Okay, and the second phase precipitates out, and eventually a two-phase equilibrium might be formed. Okay, and the higher amount of precipitates with longer aging time. Okay, aging time. Okay, now equilibrium precipitates during aging. During aging of many alloys, a continuous series of precursor precipitates forms as intermediates. And these non-equilibrium precipitates are coherent precipitates. Wow, we already know the coherent precipitate provides a good the good emphasis to block the dislocation movement. Okay, and alloy strength increases with time as these intermediate coherent precipitates are produced, and this is the age state of the alloy. Usually, the longer time for aging produce the higher strengths. Usually, of course, there's a limit of aging time. Okay, And alloy stress begins to decrease when non-coherent equilibrium precipitate is produced. At this point, the alloy is over-aging. Okay, therefore, I already mentioned that the aging is limited. Okay, so for the aging, you have to figure out the optimum process. It is not, okay, it's not means for longer time is better. Okay, so if this aging is longer when this non-coherent precipitate form and its strength decreases. Okay, stress decreases. Okay, the effect of aging, temperature, and time. The properties of aging hardenable alloys depend both on aging time and temperature, of course. Right? Using lower temperature and higher aging time leads to increased maximum strength, which is also maintained over a longer time. Okay, so how to produce the higher strength alloy by aging? Okay, use the lower temperature for aging and the higher aging time. Right? And the properties are also more uniform if aging proceeds slowly. Okay, aging slowly. And some alloys can age at room temperature. That's called the natural aging. It requires a long times, but peak strength is higher and there's no over aging. Of course, it's at the room temperature. Therefore, you have to realize that for the age hardening, it's only for the non-ferrous metal. Okay, it's only for the non-ferrous metal like aluminum, nickel, and so on. But for the ferrous metal, how to stress it? By heat treatment, right? By heat treatment, right? Or by dispersion phase. Okay. Okay, so let's look at the effects of the aging, temperature, and time. Okay, so we have to find out the maximum strength. Corresponding to its aging time. Okay, corresponding to its aging time. Okay, so if this is the same alloys with different aging temperature here, right? Okay, so if I want to get unit stress at 380, and which temperature, which aging temperature and time you're gonna use. So I want to get a unit stress of this alloy is about 380 megapar, and what's the optimal aging time and temperature you will use? Okay, I will use the temperature is 230 Celsius. Okay, 230 Celsius. Well, you may ask, well, for the temperature 190 provides the higher unit stress, right? At this point and this point. Well, similar. However, the aging time is a huge difference. It's a huge difference, right? For this temperature of 230, its aging time is about well, it's about 0.2 or 0.3 hours, right? However, for the temperature at 190, right? So its aging time is almost 10 hours. You can see the huge difference. And for the temperature 190, whose unit stress just increased slightly higher than that of the 230, right? 230. So for the cost issue, if I were the boss, I will just choose the process of the aging temperature at 230 Celsius. Okay. Okay, so the requirements for aging hardening, not all alloys can be age hardened. 4 conditions must be met. Alloy system has decreasing solubilities with decreasing temperature, and matrix should be soft and ductile, and the precipitates hard and brittle. The alloy must be changeable, and a coherent precipitate must form. Okay, and many important alloys meet this condition, such as those of nickel, copper, aluminum, magnesium, iron, chromium, titanium, and so on. Okay. So our course will stop here. Okay, and okay, so next week we are gonna have the new chapter for these courses. Okay.